general discrete time LQ optimal control problem. We have explained how to take partial derivatives for matrix, and later we talked about how to move from the general optimization problem to discrete time LQ optimal control problem. I want to start with a writing down of the central equations for LQ, discrete time LQ problem. This set of equations, you have to write it down once along the course of taking this ME233. So when you write it, you will understand more about it. Review of discrete time LQ solution. So we have a system. So in this case, I will use the time invariant system just for simplification of writing. Xk plus 1 equals A, Xk plus BUK. And our performance index, so you probably are becoming very familiar with this, is the terminal cost plus a sequence of cost along the path. Let's say we start at K0. So I'm going to have X transpose K, Q, Xk plus U transpose K, RUK. This is a performance index. From time to time, we often write this Q here as C transpose C. This is just for convenience, because if we write it this way, now think about this product term. We're going to have X transpose C transpose times C transpose X. So it's equivalent to CX transpose CX. Because we often, in linear systems, we often write it like this, Y equals CX. We are minimizing the output of the system. Okay, so that's just a common way of writing Q. Huh? So a student asked we can select this Q different from the system matrix as well if we want to minimize something else. Okay, that's totally feasible as well. The optimal control law is this: U optimal at each time index equal to negative. This is what I usually do. I write down the structure first, and then I fill in the blanks. It's a state feedback control law. And above here are a bunch of matrices that we derived last time. And the optimal cost, J optimal at time 0, is going to be a quadratic function of the initial state times P0 times X0. So state feedback law, optimal is a quadratic function of the initial state. Last time we derived the Riccati equations for this P. I won't repeat it again. This is what we discovered. We said that for this Riccati equation, we found out if we initialized this boundary condition at several, we chose multiple initial conditions for this Pn over here. And then in the end, we found the solution just always converges to these steady state solutions. All right? Now, if you think about what you learned in ME232, do you remember any assumptions for a steady state solution to exist? For these convergence, there are conditions the system has to satisfy. Someone said stability. Someone said stability. That's a closer, not perfect answer. Any other? Controllability. Any other guesses? Now you're just guessing random. No, that's controllability. If you review in ME232, these are the assumptions for a steady state LQ problem to exist. A-B pair has to be controllable or stabilizable. and the AC pair has to be observable or detectable. The controllability is for this one to converge. For the observability condition, that's for something else. In this lecture, I want to dig into some more details about this aspect. I want you to be able to understand why these conditions are needed, and specifically, what are the purposes for each one of them. Here is a short summary. Let me hide this first. Here is a short summary of what I just talked about. For this Riccati equation with boundary condition like this, it turns out, in the case of limiting this optimization frame to be infinity, if AB is controllable or stabilizable, then it's guaranteed this Riccati equation is going to converge to a bounded matrix in the steady state. This is regardless of how you assign the initial values. And that's kind of nice, because it tells us we can converge to a constant matrix. Then when we implement the control law, we can simplify the computation. This is intuitive. Remember, we are doing this minimization problem, which is a quadratic function of x and u. If the system is not even controllable or stabilizable, think about what will happen. It means some of the states we cannot control, right? So it's largely possible these states have chances to blow up to infinity. That's the intuitive meaning of not controllable or not stabilizable. So if some of the states just go wild, this guy is going to go to infinity. We can't minimize it. We don't have the control effort to place on these states. Now, we just reviewed this. The optimal cost is a quadratic function of this. If this is infinity, and we started with some finite initial conditions, then it has to be the case that its norm of this matrix is going to be infinity. All right? Make sense? So now we've talked about this convergence of the Riccati equation. Now, if the Riccati equation is going to converge, it's going to converge to this algebraic Riccati equation, ARE. Sometimes we write it as ARE. So we just have to solve this equation, which looks like a quadratic equation of P. If this is convergent, then it means our control law converges to a constant matrix, constant state feedback control law. These are constant matrices. Then it turns out it's convenient to define the cost in this way. Well, what's the difference of this one compared to the cost we introduced earlier? This cost here. We don't have, yeah, someone else wanted to say something? We don't have the final terminal cost, right? And the idea behind this is intuitive. If we're going to do this control design, when we want to minimize this, then in the end, x has to converge to 0. It doesn't make much sense if I want to minimize this, and then in the end, it doesn't converge to 0. It turns out, under the controllability, observability conditions, we can guarantee they will converge to 0. Not necessary to include the terminal cost. And that's a fantastic feature of this LQ problem. Let me read it to you. This is a wrap-up of what we discussed. Controllability condition, observability condition with this definition of Q. We can have guaranteed closed-loop asymptotic stability for this one, which is meaning x will converge to 0 asymptotically. I defined over here, I made some new definitions here. This equation comes from this. xk plus 1. This comes from axk plus buk. And then I just substitute in uk equals negative kxxk. All right? Optimal control law is a state feedback control law. So I just plug it in here. I get this a minus bk. And then I defined this matrix, a minus bk, as a closed loop matrix. First of all, we have seen this. Controllability means PS and Ks is going to be bounded, right? We have just shown this. We have shown the intuition of this. Now, the tricky part, mathematically tricky part, is this observability condition. The observability condition is going to guarantee us we're going to have the matrix P of S is going to be positive definite if the system is observable, okay, with this optimal control law and this definition of Q. Again, I'll start with some intuition for this condition first, and then we'll dig into the mathematical details. The intuition is like this. Remember, we have this cost function. Infinity, let's say. Xk, so let's say this is summation k. R, UK. So we have seen the controllability condition means we can control the state. So the final cost is going to be finite, all right? And the observability conditions make sense in this way. If the system is observable, it means we can see how the system is going on from the states, from this cost. The meaning of observability means from the output measurement. I've told you if Q is defined as C transpose C, then this whole term looks like Y transpose K, Y transpose K times YK for this term, right? I have explained to you that if the system is observable, then it's intuitive that we can see how the states are going on from the output. That's the intuitive definition of observability. We can see how the system is going on from the output, all right? Now, if you buy that, then this makes sense. If we can see how the states are going on from the output, then if we are minimizing this, it's intuitive to say that the closed-loop system will be controlled to be stable. We'll dig into some more details about that. Okay, the first step to show this observability implies P is positive, definite, is to do one step in the cost function. Is to restructure this performance index in a little bit different way. You remember that this U, this optimal control law, is negative Kx times Xk, right? If you plug in this one here, then you're going to see this cost is nothing but one quadratic function of x, another quadratic function of x. So you can massage these two terms together. It's going to be a big quadratic function of x over here. And the inside, this matrix is slightly different. So it's a combination of these first two. It comes from these ways. First of all, substitute Q to be equal to C transpose C. Then I'm going to have one term, X transpose times C transpose times C. So this is the first term. And then the second term comes from over here. This matrix occurs like this. From this substitute UK to here, we're going to get X transpose K, KS transpose R, KS, X of K. Right? Now, R is positive definite, so I can deconstruct X or R into this combination here. And then it's because of that, combining these three terms, we get this one here. And then the rest of the terms is the transpose of this term. Everyone sees that? This is a classical way to massage this cost function. As you do some more examples, you will get very familiar with this. Now, we have explained X of K, the dynamics of X of K is this one, right? This is the closed loop dynamics of X of K. If I just give you this equation here and I ask you, what's the mathematical solution for x of k? If I just give you this one, I give you the initial condition, I give you this dynamics of x of k, what's the solution? So the question is, let's say, take one more simple example. If, let's say, xk plus 1 is 2xk, initial condition is x0, what's the mathematical formula for xk? To power of k times x of 0. Right? Yeah, that's what I was asking. So if I give you this, what are the solutions for x? So the solution for x of k is this. For this general equation here, xk equals a CL k x of 0. Okay? So do this step. After you obtain this, substitute x of k as the solution here. Then you get this. Now, the summation is over k, so it doesn't depend on x of 0. I can take this one out, and I can take this one out. So I'm going to get this. Okay? If you recall, this matrix, this WCL matrix, which equals to, from the definition here, 0, summation from 0 to infinity, ACL k transpose C R KS. So I'm going to ask you the question once I finish writing. What is this matrix WCL? PS. That is correct. You notice this one. WCL is going to be PS. There is another side of this story here. This matrix is also the observability grammar of this matrix here, of the system here. All right? That is something very interesting. So we have translated the performance index relating to the observability grammar of some new, this is the closed loop, new closed loop systems. Now, if the original system is observable, what do you think this one will be? This new system will be? Guess. If AC is observable, have a guess what will this one look like? The conclusion is correct, but the analysis is a little bit not rigorous. So someone said it's going to be observable because it contains a C. Partially correct. Maybe if the score is 10, I will give you 3 to 4 points. Anyone wants to take another look? Full rank of what? If we constructed the observability matrix, it's going to be full rank. That's what you imply. So if we want to test the observability, we have several ways. We can construct the observability matrix, right? And then check the rank. That's one way to do. I want to show you that this is actually makes sense without going to the observability matrix construction. Okay. The first thing to look at is this. Maybe this is the first thing to look at. If the original system, AC, is observable, I just do one more step and construct this system. Think about it. This system has to be observable because the state dynamics are exactly the same. I'm just adding one output. I'm just adding an extra output over here, right? You notice everything else is the same. It's the original system. I'm just adding one output. So if I can already observe the states from this output alone, if I add one more, I will definitely be able to observe the states. So if AC is observable, then this guy has to be observable. Now, I was asking the observability of this guy here, which is the same output, but the state dynamics is a little bit different. But it doesn't matter because this one is the closed loop system of this guy under a feedback control law. So if you notice, if I substitute U here as a, let's say, as some kind of feedback dynamics, I'm going to feedback the output y tilde here. So let's see, what will be the feedback gain here? I look at this, so I see I need to some terms that contains k of s to make this happen. And this guy doesn't contain c. So I'm guessing the first one has to be c, has to be 0, and the second one has to be negative r negative 1 divided by 2. Let's see if that works. Okay? So if I substitute this is the static output feedback control law to this open loop system, then I'm going to get AXK plus BUK, but there's a minus sign, it's going to be minus B R negative 1 divided by 2 times this element here. So it's going to be KS X of K. So you see, this system is nothing but this open loop system controlled under static output feedback law, right? You can do this again and again. Look at this long enough, you will buy this. If you recall, observability is invariant under static output feedback law. That's because if I see, it's again this analogy, if I can see the states from the output, then no matter how I massage the output into the system, I will still be able to see the states. So that's this picture here. Now, if this is observable, what will the observability Gramian be? Positive definite, right? So that means this. That means this matrix WCL is positive definite. That means PS is positive definite. Take a look at this again and try to have a quick memory of this. AC controllable or stabilizable means the Riccati equation is going to converge to a bounded steady state. And then if we have additionally the observability condition, then this one will be positive definite. The reason why we need this positive definite matrix, think about, for example, Lyapunov analysis. In Lyapunov analysis, we have a P matrix which occurs in the V function, Lyapunov candidate function. We want that matrix to be positive definite, right? Just basic Lyapunov analysis. Now, P. We want this one to be positive definite. And this is exactly what we have done here. And if this happens with certain additional conditions, you can guess the closed loop system is going to be stable, right? Because we can find a valid Lyapunov equation. Coming back to the first two statements are the tool sets to conclude the closed loop stability of the system over here. I'll start by recalling this algebraic Riccati equation over here. I mentioned to you that if you look at this is sort of like a quadratic function of P. And it looks actually very much alike a Lyapunov equation. If you recall standard Lyapunov equation, what's over there? PS equals A transpose PS A plus Q. Standard Lyapunov equation. And we just have some extra term over here. And my next purpose is to explain to you how this guy can be massaged into this Lyapunov equation. And then if I can do that, and then I found this guy is positive definite, that means I have a valid Lyapunov equation to conclude the closed loop stability. Let me ask you one more question. If I want to conclude the closed loop stability, if I want to conclude the closed loop stability, what should be my matrix A here? I intentionally said it's A tilde to let you not think it's this matrix. It's something else. If I want to conclude closed loop stability. It's going to be the closed loop A matrix, right? It's this one, so which equals A minus BKS. So the next step, if you see that, then the next step here is doing nothing but add and subtract terms. This is my goal. I want to, in the end, arrive at something that looks like this. All right, you see the structure here. PS, A, transpose PS, and then something else. Okay? This is, we're going to talk about this detailed math later. But if you see that we can arrive this, and we have shown PS is positive definite, then what does that mean from this Lyapunov equation? This matrix here is always positive semi-definite, right? So that means in this Lyapunov equation, we have found something that's positive semi-definite, and this is positive definite. That means the system is at least stable in the sense of Lyapunov, right? After a few more algebra, the system turns out to be even asymptotically stable. But that's the big picture. And details you can read back in the notes. These details are doing nothing but first of all, I want something, in the goal, I want something Ks transpose Ps Kx. So I have to somehow generate a quadratic term of Kx. This is what's happening here. So from the first step to the second step, I'm adding and subtracting this term here. Not adding and subtracting, but adding this guy and the inverse of this guy to make it happen, to make this term occur twice. Okay? And then from here to here, I'm just constructing this one. I'm just trying to see what will make out this one. So I first constructed this, and then I add and subtract terms to make it equal to what I had. Okay? So these mathematical details, it's enough. You have seen it once and know how it works. What's remaining to be done? I've shown the system is stable in the sense of Lyapunov. I have to somehow conclude it's asymptotically stable. So that's one more step. And I will show you this powerful theorem. It turns out this is something that's used in a lot of places. This is an extension of Lyapunov theory based on observability. It says this: if we find from Lyapunov equation, this is a standard Lyapunov equation, where P is positive definite, Q is positive semi-definite. And if we write Q as in this form, and AC is observable, it turns out that the system is asymptotically stable. This is exactly what I have just done. I have constructed a Lyapunov equation where this P matrix is positive definite, and this Q matrix, if you recall, is positive semi-definite, as written down here. But we have shown that this system is observable. So immediately we can apply this theorem to say the closed-loop system is asymptotically stable. We can come back to the proof of this part, this theorem, if we have time. For the moment, the proof is actually not very difficult at all. And it's easily understandable. If we have time, we're going to go back to this. Now, I want to give you one example to see why this all makes sense. I have this first order system over here, written down over here. Xk plus 1 equals 2xk plus uk. Is this system stable? This one? Not stable, right? Okay, we will use this. That's just an observation. So let's say if I choose Q and R in my performance index as 0 and 1, these are all valid, right? Because R is positive definite, Q is positive semi-definite. Okay, these are all valid assumptions. What do you think if I'm minimizing? What do you think? What's the optimal control law? Let's say summation from 0 to infinity, xk transpose q xk plus u transpose k r uk. What do you think is the optimal control law? If q is 0, this guy goes to 0. What's the optimal control law? U has to be 0, right? That's the way to minimize this. So that means we are doing nothing. We are not doing anything to the system. And the reason for that is, again, if this is 0, if I define Q equals C transpose C and Y equals CX from this output, we cannot tell anything of the states because this guy is 0. Okay? So if we can't tell anything from the states, then there's nothing we can do this minimization here. So you see, the optimal control is 0. So if that happens, you see, the closed-loop system is not stable, right? What conditions are failing here? I have explained that if some conditions hold, the closed-loop system is guaranteed to be stable. What conditions are not correct here? You see immediately, right? Is the system controllable? Yes, right? Because A is 2, B is 1. The system definitely controllable. So the observability condition is failing here. And as a result, the closed-loop system is unstable. So hope this convinces you that these conditions are good. These conditions are required to have a meaningful solution. So these are additional summaries. This slide, I just want to show you LQ problems. Steady-state LQ problems have excellent closed-loop properties. I have shown you in a little bit detailed equations. It has guaranteed closed-loop stability. But from ME232, if you read the notes over there, you will see it has excellent margins for single input systems. We have these margins over here. And then we have guaranteed stability for loop gain changes. So this is just showing excellent closed-loop properties. LQ is good in this sense. The details are in the ME232 class reader. As a summary, someone is still taking notes? Okay. As a summary, think what we have done for up till now for the class. We have reviewed the general discrete-time LQ problem. And then from here, we did a double integrator example. This is to show you that P, K converges to a steady state solution. But I was hiding this information here that double integrators are controllable and observable. That's why it happens. And then later, I showed you why, when this is guaranteed. So now you have seen AB, controllable or detectable. So, and then over here, later we showed its properties. If adding the AC observability conditions, we can show it has excellent properties. This is a quick summary of a discrete-time LQ problem. Any questions